So thanks for coming to this talk. So I'm going to talk about computer vision. And how many of you came across computer vision before? How many of you do experience? Okay, very good. So I'm going to have a brief introduction of what computer vision is. So it can be seen different ways. So here is one possible way to define challenge. We have a video. You want to have a natural video. You don't want to recognize just laboratory setups. You eventually want to say what objects, what actions are happening, what scenes, something like this. So this is quite complicated, as you can imagine. So here is the same scene. If you now convert it to numbers, that's what computer sees. So that's kind of one projection of why the task is done. So nevertheless, there's been quite a big progress on this topic recently. So maybe some of you have heard about convolutional neural networks. So the numbers here is they talk for themselves. So there's been computer vision before 2012 and computer vision now. So object recognition is one of the historically major tasks in computer vision. And so for this task, since several years, there is one benchmark which is particularly important because it led to big improvements. So this task, so before 2012, so these were the error rates. And so here really people were fighting for like 0.5%. And so what happened in 2012, that there was a method which beat the previous method by about 10%, and then since then, so we have quite a big improvement. So what's the task? So it's object classification for 1,000 object categories, like their parts, scooter, and so we are given, say, hundreds of thousand images. So the computer should put a label on each of them, and then if it's wrong, then the computer error rate. So interestingly, so there are people are not perfect on this task. So you can just take a person from the street, ask whether, of course, these two images are easier. If you would know how to call this image, it's already harder. So people basically not perfect. So they do about 5% error rate. Although also there are problems with annotation data sets, so it's not probably cannot be solved for 0% error rate. Nevertheless, so this rapid improvement here shows that there's been lots of progress in the last years, and not only in object recognition. So once we had this system to recognize objects, one could start with lots of other different things. For example, face recognition, but also object segmentation, video recognition, and so on. Okay, so again, here similar situation. So we have what is face recognition? You can pose it as just classifying each pair of images if it's the same person or not. And okay, so again, so before deep neural networks and after, so numbers changed quite dramatically. Again, the human performance is not perfect, and currently there are methods which are actually doing better than that. Because of this, so these are academic numbers, but actually they translate now in technology which can be applied in real life a lot. So this was not the case, say, 5 years ago for this type of technology. So here's an example from the VisionLabs company which we work with. So there are cases in banks where people come to take a loan, and so banks can now recognize that this person already was there, but it came before under different name, right? And it's probably the case where the person has a falsified passport or something like this. So this technology actually, in case of banks, it can be translated directly into revenue, because if you stop this person to take the second loan, the banks will some money. Okay, so but actually what I want to talk today about, not much applications, but technology, and especially what are the interesting future technologies which we still need to develop to progress. So let's look at what is the convolutional neural network. So it looks complicated, but actually it's not That's complicated reality because it consists of several layers which repeat themselves. So there are single operation each layer, and so there are algorithms to train these networks, which are also quite simple. It doesn't mean that these networks are simple to understand. Actually, nobody has a good analysis of what happens inside, but to use them, they are currently became quite simple. So, so these networks, they're very heavy, so they have about 60 million parameters in this case. Obviously, now, if you know, well, even if you don't know about machine learning, so if you have some system which has lots of parameters, to set these parameters you need constraints, and constraints typically provided by the data. You can hand-engineer some constraints, but if you want to recognize a car or any object, people try to hand-engineer it for a long time. Currently what works is actually the neural networks which try to learn it from the data. Okay? So, and the neural network actually provides the mechanisms to learn the whole system from beginning to the end, given the data. Right? So data in this case are images, it could be videos. Right? So data is definitely a very important ingredient. Another important ingredient which makes the thing work is computing power. Currently this is done on GPU, much better than CPU at the moment, at least for training. And the last part, but not least, is the annotation. Because when you pass through the data through the network, okay, you can do it fast with the GPUs. Now you have to compare the output of the, during training, you compare the output of the network to some annotation which somebody provided to you. And this is crucial because when the network is trained, so here you compute the error is backpropagating and updates the parameters. So what I want to point out is that now what are the critical parts of these ingredients? This is free, you can have it as much as you want. This becomes cheap, and eventually we will have a lot of it as well. Here, this is the problem because this is provided manually, so you have to manually label the images, and this it just has the limitations. Right? So we have a limited number of people on the Earth. Nobody wants to work for free. So there are major problems with this annotation. So first, it's expensive because say we want to solve a task of detecting objects in the image. Okay, so detecting means putting, for example, a bounding box around. So it means that somebody has to provide the bounding boxes for us. So that's hard. If you want to do it for one object, maybe you need a million examples, 1,000, say in order of 1,000 examples, but then for each new object you will need the same. But second is that the labels are not even well defined because what is this? You can say it's a table, dining table, it's a desk. So to further illustrate the point, so question to you, what action is this?
Running.
Very good. What is the action? So this is to illustrate that just labeling thing it's not just hard, it's also very ambiguous. So especially for action, so how to define action, it's an open problem, and I hope if I have time I'll talk about this. Okay, so this motivates the talk. We want to design methods which train the system in a weakly supervised way. What does it mean? We don't want to provide too much. We may provide some annotation, but we don't want to provide exhaustive annotation for during training. By the way, if you have any questions, doesn't bother us keep questions. Okay, so let's take a concrete example. You want to say detect objects. Say somebody was nice and gave us lots of bounding boxes for chairs, for people, for everything. So that's great. So we can just take a network. We can sample the patches from so cut out all the objects from the image, put it through the network, train, easy. Nowadays you just download the package and it does very nice things. for example, like this. So now this is a test time. This image has never been seen during at the training. You can create, say, heat maps which roughly tell where particular objects are. So, say, for potted plant, this is quite a hard example. Maybe you can project this a bit dark, but you can see it back. Right, so it localizes the person, then they go. And so sometimes it does surprising things. And so for this image, you see there's a high response for a bus. There's a weak response for a car, and actually a car is over there. And there is some strong response for the person. And if you zoom in, yeah, you're okay. So you should see the person. So it does really work. It works much better than what we expected. But than what I would expect after being 10, 15 years in the field. So, but still, we are not. This is not the goal of the talk. The goal of the talk is actually to go away from manual supervision. So, what if we are not given these bounding boxes? So, can we avoid this difficult supervision? So, can we live without it and just train the network? Why is it interesting? Well, it's already interesting because if you just say the image has a car or not, this is easy to annotate, but actually there is plenty of data on the internet which may allow us even do completely automatic supervision. Because if you are given images like this, right, so somebody was nice annotating just not for computer vision task, but for some other purposes, putting some sentence describing this image. So from this sentence we can distill the information that bicycles should be there. So can be trained from this textual supervision and images to really build the concept what is a bicycle. So that's will be the first part of the talk. So to formalize a bit, so here we don't, in this part we don't deal with text recognition. So we just will assume that given an image, we are given a list of yes/no answers, so whether this image contains a person in a chair, or if the person is reading or not. And then at the end, at the test time, so we want something like this. We want to localize the object, of course recognize, localize the object, or action. Okay. So turns out this is actually a very simple mechanism to do it. So I know I have not explained what the network is, but so just imagine that this is a level of operations which at the end give a score for the whole image. Now we can think of it as subdividing image into parts, so that at the end we are not giving a score for each object, but we are getting a heat map, getting some score map for, so each map here corresponds to one object class. Okay, so if you know that there's a motorbike in the image, we assume that the corresponding map for the motorbike should score high somewhere. And that's how we are going to train. So we're going to, this max, this is essentials, we're going to max. We are going to assume wherever the network is firing, this is going to be motorbike. The network doesn't know where it is in the beginning, but so if you're familiar with machine learning, so you may know term multiple instance learning. So actually what this max operation does, it does some sort of multiple instance learning where we don't know where to search. So there's a latent variable of location, but by maximizing the output, we are resolving location. So next video shows what happens at training time. Right, so these are images of all of them of motorbikes, and in the beginning everything is blue, playing it again. So network knows nothing, and eventually with more iterations during training, so it tries to localize the object in training images. And once it can do it in the training images, of course it can do it also in test images. Here are some examples. Here we try to recognize 80 object classes in the Skolkovo dataset. Okay, so it works well. Of course, always interesting to look at mistakes. So here's one who thinks this is a bench, which probably correlates with person sitting. So we, of course, we've never trained it for sitting, so but it's somehow picked it up so that bench probably correlates with people being sitting. Although it doesn't explicitly have not been learned on the concept of sitting. So here's more example, and again, this is an interesting mistake. You don't see it, but this person actually does not have a tie. The system predicts the tie. So what's interesting, it predicts it on the right place. It doesn't predict the tie somewhere on the sky. It predicts where it will be. So same thing actually works also for, not just for objects, but exactly the same method works for actions. If you now have a data set where somebody said these images have plane instrument at the training time, then you give other images to the test, so and it will roughly localize where it is. And again, so so probably in the back, I don't know if it's, can you see what this is? So this is the pizza box, yes. Okay, so the mistakes are actually quite human. So they are not concluding that we have done natural intelligence, as there was a panel just half an hour ago. Actually, maybe with switching off the light was good. Okay, so one more step. So actually, what we've done, we have localized we put the cross on the object. It works good, but we don't know the scale. We don't know the extent of an object. So more typically in computer vision, people when detecting objects or localizing objects, people talk about bounding box. So putting something like this around each object. So that's what we want. This is harder because this has more degrees of freedom. So it's we just not need to estimate location anywhere. We need actually to know where objects begins and ends. But obviously that's more information. So if you want to jump on this horse, then you should know its extent, if it's this big or that big. Okay, so trying to look how to reduce this. So actually there are methods trying to solve this problem. The typical problem for this task is that the network or any method will actually locate the discriminator. So it will locate things, and maybe you've seen on the previous slides. So it's usually will find the discriminative parts. Like for cat, it will find the face because this is the part of the cat probably which is most easier to discriminate from everywhere else. Okay, but actually finding the extent, and so the same here for the horse. Finding the extent of an object is a more difficult problem, and that's what we try to do. This is a recent work and submission. So we are not looking only at the information inside the bounding box. We are also looking at the context around it, and so these two measurements. So we measure image at some window. And we do another set of measurements at the boundary around the window. And so while training the network and constraining the weights of these two layers to be the same, so actually we can do the contrastive model. So one we try to shrink the search, another we try to expand, and at the end it will localize things much better. So I guess I don't have time, unfortunately, to go into details. So I'll just show results. So results on two data sets are good. So this is our method, other methods around, which we all perform, and qualitatively it looks like this. So where we had the head of the horse localized before by other methods, so we are doing much better. In many of these cases, we are doing better, which you can see also in the numbers. Okay, so how many minutes?
We have time for questions. If anybody
actually, so this was just the first part. How much time do you have?
5 minutes.
5 minutes left?
Yeah.
I see. Okay. Let me just then. So the next part actually was about video, and maybe I'll just very briefly walk through it. So we want to, as we did, as we recognized objects, so we also want to recognize actions in video. There are many reasons to do this. Since I don't have time, I'll switch through some things. So I'll just show you some results. So we're interested in movies, to recognize actions in movies. So this is just a playground for us to understand how to develop algorithms and test them. So here's a system which has been trained for, also in a weakly supervised manner, which has been trained for recognize 16 types of actions. And recognizing also localize. So before I talked about localization in images. So here, the system, what you see here at the bottom, the system localizes when the action happens in time. Okay. So it's been partly done with in a collaboration actually with Skolkovo. So VisionLabs and Skolkovo has a joint project which also does neural networks, but in this case, the neural network is done for video. So video can be processed either as pixels. It turns out it's good to process the video also by taking the motion vectors as input. It produces better results. So we have methods which does well on some benchmarks, and in particular it does it fast because computing motion is very expensive. So what this network is doing, it takes the motion from video encoders, so it doesn't need to spend any time on computing motion and still can reasonable good results. I imagine I have to. Okay. Oh, I see. Great. Okay, so it's still 3 minutes. Right. So the last part I want to talk about is so what are we? So it's more open-ended question. So are we trying to solve the right tasks? And so here's a question. So what is an action? Is it the right way to address action recognition quite lately? So here's one extreme example. We have action open, which can mean lots of different things. Okay, this is another fun video which I like to show in this context. This is a private surveillance camera in UK a few years back. Some of you have seen this video. Have you seen this video? Okay, so the people were missing a cat, so they, for some reason, they looked at their surveillance camera, so they found this. So then they found the cat, and then police found the woman, so everybody was happy. So if you don't like surveillance for privacy reasons, so this is your cat, you will be willing computer vision to help you. I'm sure. So here currently the solution which I can propose to you is to currently the computer vision solution would be to train a person throws cat into trash classifier. I imagine we can do this. Probably won't scale very well. So there is a problem here. So we have a granularity. What level of granularity should we take? We don't know, and actually I think it's not known until you go and define the action with respect to some task. Okay, so we are doing things to achieve some task, and this seems to be crucial. So therefore, in the part which I don't have time to talk about, so we looked at but okay, I'll show one slide because it relates to robotics. So we tried to learn a system to understand what it means, the instruction videos. We download a bunch of instruction videos, say for changing car tire. And now I want the computer to learn what are the main steps of changing car tire. And the task is not just visual, it's also text, because people narrate. This helps us, so people tell, okay, now I'm doing this, this, this. And if you have 50 videos of this type, then you start to, because they will be redundant, so you will search for redundancy in images and in the text, and you will be able to learn it. So why is it good? Imagine in the future, so if the computer can just learn from internet how to do things, you plug it into a robot, and then your robot change your car tire, for example. So I believe, okay, I think this will come, maybe not tomorrow. I think what we are much more close is more this setup where you have a personal assistant. So you can have personal assistant now, say if you have HoloLens, and you call best cook in Russia, and he will tell you how to cook your best dish. Okay, this is possible. So what if we can make assistant which can automatically guide you how to make things? So this in some, you may even now personalize, but especially also for professionals who has maybe limited knowledge, it could help a lot. So I won't talk about details. I will just again show just the demo video, which so what it does. So it's similar as I showed before, but here we really not just trying to recognize actions. We are discovering from the narrations. Okay, sorry, so I will just go back. So that's how the data actually looks like. So this comes from narrations. These are corresponding images. So we are trying to solve the clustering. We try to cluster the text and cluster the video together, and to try to find the correspondence. So what does it mean to tighten one nut or screw or so on, without any additional information. And once this is done, so this is a demo video in the So here are the steps which were discovered in text and also in the video. So, and just one last slide about things which I think completely open, so we don't know how to do them. So imagine you have this image and this question. Actually, this is not so unusual. Do you know what this is? Yes. Right. So basically this type of questions, you can call it, since we cannot do it, we can call it intelligence. I think it will be solved in 5 years, so we won't call it intelligence anymore. Because computers are stupid. So I think, okay, these are the unsolved vision problems still.
Thank you.